there are really two types of indefinite improper integrals. And the first kind is called the infinite interval one. What it means is that we have now a definite integral from somewhere a to infinity. So this is, if you look at where the function is defined, is from somewhere a, and there is no really an upper bound b over the upper limit, and you have a function f of x dx. Okay. And the essence of this type of integral is that it's really a combination of two mathematical concepts. One is the limit. So it's really about, you take a limit and the integral is going from little a to capital A and f of x dx. And this is the kind we know, it's the definite integral. So after you take the definite integral, then you let capital A go to infinity. So this is something we are familiar of, and we can just look at some examples and then pay attention to special places that we actually need to be careful of. So let's look at an example over here. For example, over here what we have is from 1 to infinity and 1 over x squared and dx, right? So by definition, this is equal to a limit over here, and then here we say let capital A go into infinity and from 1 to capital A, and then we integrate 1 over x squared and dx. Now we integrate first, so what we have over here is that capital A going to infinity, and then here we have x to the negative 2. When you integrate, you have negative 1, x to the negative 1, and you plug in capital A and a 1. And that will give us the value of the definite integral. When we plug into A, we have negative 1 over A. Okay. And then when we plug in 1, because of this negative sign, we have a plus. So we have plus 1 to the power negative 1 is still going to be 1. Okay. So now look at this limit. We can easily see if A is approaching infinity, this limit is simply 1. And the meaning is quite clear. We have a function defined over the interval from 1 to infinity over here, and the function is 1 over x squared, so it looks like this. And this function is 1 over x squared. So the meaning of this indefinite integral is the area beneath this bar, beneath this curve over here, and it goes to infinity over there. Okay, so that's the meaning of an improper integral. Okay, so this is our example 1. Okay, now we can combine the integration skills we just learned with this type of problems. So let's try another example. You can also have the improper integral from negative infinity to somewhere. So you can also do an improper integral, something like this, from negative infinity, say, to 0. And let's make an example of integration by parts so we can also review. And then this is x times e to the, let's say, make it harder. In our textbook, we have just e to the x, but let's try to make it a harder problem like this kind. And since now the infinite interval is from negative infinity to 0, so now we have the following limit over here. We make the lower limit over here to be a, and upper limit is 0, it's a normal number. And then you put you let a go to infinity, right? And then integrate x to the e to the 2x and dx, right? So be sure to copy this limit because it's an improper integral. We need to have this limit. But for this definite integral, we need to use integration by parts. We integrate this part first, and then we have the following. Just copy over here a from 0. And when we integrate e to the 2x, we have 1/2 e to the 2x. Okay, that's what we have. And then we apply integration by parts, and then we have limit over here. A is approaching infinity, and then we have from let's erase this part over here. We apply the integration by parts. So we multiply these two functions, one in front of x, d, the other one is behind d. So we have x over 2 and e to the 2x, and plug in 0 and a over here. Okay, and that's the one. And then we subtract the integral, swap them. So we have from still a to 0, and we have 1/2 e to the 2x and dx. Okay, so what we have is the following limit. Limit a is approaching infinity, and when we plug in 0, we get a 0. Now we need to look at what's going to be the limit of a when a going to infinity. A over 2 and e to the 2a, but a goes to negative infinity. A goes to negative infinity. We need to make sure it's negative infinity, not positive infinity. Okay, negative infinity. A goes to negative infinity. And the second integral over here, now we can find out that's going to be minus 1/2, another 1/2, and e to the 2x. Again, we plug in on 0 and a, right? So we have the following limit. This is the one. Limit a is approaching negative infinity, and negative a over 2 and e to the 2a over here. When we plug in 0, we get negative 1/4 e to the power 0, which is 1. And then we have plus sign because it's the lower limit, and then 1/4, and we have e to the 2a over here. So we have 3 terms over here. We need to find limits. But it's clear to us that this limit over here is 0. Limit a going to negative infinity e to the 2a is 0, because that's the exponential function's property, right? And we have over here the following. If we let a go to infinity, then we have negative 1/4 for the middle one. And then we need to look at also this limit. What's going to be the limit when a is going to negative infinity, and we have a on top, and then we have e2 over here and e to the 2a. We need to use L'Hopital's rule to determine this limit, because a is going to negative infinity. This is so-called infinity times 0 type. Okay. And the easiest way to find the limit is using the L'Hopital's rule. So this is going to be limit over here, and a is going to negative infinity. It's easier if you put a on the top, and then you put e to the negative 2a at the bottom. That way, when a is going to negative infinity, negative 2a, it's going to positive infinity. So this now becomes infinity over infinity type, right? And then using L'Hopital's rule, we can take the limit, and then in the following way, take the derivative. That's the L'Hopital's rule. Takes derivative with respect to a. So this is 1 over here, and then this part will negative 4 e to the negative 2a. Now if you look at this limit, the denominator goes to infinity and numerator is 1, so the limit over here is 0. So finally we have this answer from negative infinity to 0 and x e to the 2x dx. This improper integral is equal to negative 1/4. Okay. Now after we finish, we try to see if it's reasonable. And think about x is negative between negative infinity and 0. E to the 2x is positive, so the value should be a negative value. Okay, so that's going to be fine. Now, we looked at separate cases. We have two integrals. One goes from 1 to infinity, and the other one goes from negative infinity to 0. What if we have an interval from negative infinity to positive infinity? We can do the same thing. But remember, this integral over here, if we have negative infinity to positive infinity, and f of x dx, it's defined by two limits. It's defined by the following limit. It's first of all, you actually divide them into two integrals, one from 0 to infinity, and f of x dx, and plus another one from negative infinity to 0, and f of x dx. And we calculate these two improper integrals separately. So we do calculation separately. Calculate them separately. Okay. We will use another video to show an example of this kind.